quick introduction. Well, I'm Daniel, as already mentioned, working for Portworx. So we are one of the leading companies providing data platforms for Kubernetes. But the more interesting thing for me is who are you? And maybe you should not introduce everyone by yourself. So who's running Kubernetes in production right now? Okay. Who's running stateful workloads in Kubernetes? It's not. Oh, it's still many. Who's already running virtual machines in Kubernetes? Not Kubernetes on virtual machines in Kubernetes. Okay, two. Oh yeah, I know you. And who's validating to run VMs in Kubernetes? So who thinks about and thinks about it might be an option? Oh, not that many. Okay, quite interesting. So these questions were just about me talking a little bit more about some things and less about other things. So, but in general, I can't change my full agenda now. But I will talk about storage and state in Kubernetes in general. I will also talk a little bit about running VMs in Kubernetes, why and how. And I will also introduce, as obvious, Portworx as a data platform, so where we could help you in running state in Kubernetes. So let's start first with storage in Kubernetes. Many of you are already running stateful workloads in Kubernetes, so I guess you are still aware of many of those things. But for all of those who are not running currently state in Kubernetes, first of all, Kubernetes started as stateless. This means it could manage and orchestrate containers, applications. But in the first start, many people don't do state, which means your applications run inside Kubernetes and they get data from somewhere outside, process this data and store it somewhere else. And somewhere is out of the Kubernetes cluster. And this is usually the point where many people start with Kubernetes. And in this phase, they usually have to learn a lot of stuff because Kubernetes is a beast. And you need to integrate it into your architecture, learn how it works, how to lifecycle, and all these things. So you don't focus on storage in this first stage. But stateless here means if your pod is crashing and even if it consumes temporary storage in the cluster, the data is gone. And if the pod gets rescheduled, it gets new volumes, new temporary data. As soon as you have managed to integrate Kubernetes into your processes and your developers will adopt on this, they might start with requests, okay, I want to run a MongoDB, a Cassandra, an etcd as part of my application, and I want to deploy it within the cluster. So I want to lifecycle the whole thing, my application and the data service I need. And that's the point where most people start thinking about state in Kubernetes. Because if you're running a database and the database pod crashes or gets updated, it might be useful that this new instance of the pod sees the same data as the old instance, because otherwise your data will be gone. So the way how to consume storage in Kubernetes, and it's another abstraction which is inside Kubernetes, is a persistent volume claim. So whenever a developer wants to have storage, persisting storage, which survives a crash or a restart of the container pod, the developer or application owner creates a persistent volume claim. And it just tells, okay, I need this amount of storage, and it references a storage class. Storage classes describe how storage is configured, which features are needed. So it's another abstraction layer. And the combination of both, so creating the persistent volume claim, referencing a storage class, will result in a persistent volume. And this is the volume which is separately managed from your deployments, separately from your containers. And it will survive a restart of a container. So this is basically high level the way how Kubernetes persistent storage works. If we take a more technical view into this, this is how it looks like. So the persistent volume claim, it's a YAML spec, which just requests storage. It has labels and references the storage class, and the storage class itself describes some features. It has a provisioner, meaning there's a technology, a driver, which actually creates the volume, wherever this is. And it sets some parameters for the volume. And in the end, if you're using Portworx, for example, you can do a kubectl, get PVC, and you would see, okay, there's the volume, it has a name, it has a capacity, some configuration options. And also, if you take a look into the, let's say, low levels of the storage solution, you can also see more details about this. So actually, there's one error. If someone spots it, we have a present for you. But let's go forward. The approach of how to attach storage to Kubernetes usually is to use CSI. CSI is the container storage interface, which is an abstraction layer which allows drivers from storage vendors or other storage solutions to connect to Kubernetes. We see some challenges in this approach, but in general, it's working at all. So challenges we see is usually if customers start with Kubernetes, they often tend to do the same things as they did in the past in their IT infrastructure. So they might say, okay, I already have a storage array. Why not directly connecting this storage array to the Kubernetes cluster? This can make sense in some cases, but usually we often see challenges when it comes to scale. For example, if you have a driver, a CSI driver from the storage array vendor, usually you have a one-by-one Kubernetes container volume to storage volume mapping. This means if a developer or application owner creates a PVC, the backend storage system will create a volume for it. We've had customers running this very successful, but when it came to scale, when they tried, okay, now I need to scale up my application. Now this application gets really important, and I go from a dozen volumes to hundreds or thousands of volumes. They experienced that classical storage systems are not built for this scale. Creating 1,000 volumes in a short time, and just as an example, one of our customers tried this. So now a Portworx customer. They tried to scale the application, do an automated test, going from a few dozens volumes up to a few thousands. And this test failed because of another reason, and they stopped the test. It was automated. They fixed the bug and restarted the test, and then the whole environment crashed. Why? The storage system underneath wasn't yet ready, creating the first thousands of volumes. Also haven't deleted these and was not able to create another 1,000 volumes for the second iteration of the test. So the learning of this was storage systems are not built for heavy metadata operations. They are built for bandwidth, for latency, for capacity, but not for creating thousands of volumes in a short time. So this was a technical issue. And by the way, also many storage systems don't have rate limiting on their APIs. Interesting learning. But another thing we also see when it comes to scale, when it comes to hybrid architectures, so having multiple Kubernetes clusters on multiple platforms or even multiple Kubernetes distributions, that storage is dependent on the underlying infrastructure, on the underlying hardware. And this means storage can look different depending on which platform you're running on. If you're running an k8s cluster, storage is usually provided by a CSI driver from Amazon, so it consumes EBS volumes. If you're running on-premise, your storage vendor might have a CSI driver. And this would mean in this scenario, you would have two platforms and two different CSI drivers. CSI is a standard, yes, but it usually implements basic functions like create volume, attach volume. Snapshot volume is voluntary. It doesn't need to be implemented in a CSI driver to be a CSI driver. So it could happen that in the one platform you can do snapshots and the other not. And even if you can do it in both, there might be annotations you need to set on the one platform to do consistent snapshots, and you can't do these on the other platform. So this means you have different configurations on different platforms. Kubernetes was about standardizing, right? Standardizing, automating. Now storage looks different on each of your platforms. Could be an issue when it comes to scale. And the last point here, storage arrays, if you reference to direct storage arrays, are managed independently from Kubernetes clusters. So usually if you have a storage array in your on-premise infrastructure, you have a storage team. They know the storage vendor. Now they have this CSI driver. This CSI driver gets handed over to the Kubernetes team. What happens if this CSI driver isn't working as expected? Who's opening the support case? The Kubernetes team don't knowing anything about the storage system, or the storage team don't knowing anything about Kubernetes. This is something which needs to be fixed before you go into production. And the general idea how to solve this was a container-native storage approach. So meaning to provide storage to containerized workloads. The storage solution needs to be ready to scale. That's the first and most important thing. It needs to be able to work with many small volumes, because this is about scale out. But it also needs to ensure that you have a consistent storage experience on each of your platforms, independent from the underlying Kubernetes distribution, platform, IT architecture. And it needs to be decoupled from this platform underneath, because otherwise there might be dependencies to a hardware system within your Kubernetes cluster. Think of you have a CSI driver from the storage vendor of your choice. The storage vendor updates the firmware, says, okay, you need a new version of the CSI driver. Yes, here it is. Oh, this new CSI driver doesn't work with my Kubernetes cluster version I'm currently using. So you first need to update the Kubernetes cluster before you can update the storage system. This is what blocks innovation and speed in IT organizations. And you need to think about a solution which is independent from underlying hardware, which just consumes standardized interfaces how to consume storage. And yeah, quick hint, we can do this. So we can provide this. So we provide the same level of storage regardless of the underlying infrastructure. We provide scalability, and we are managed as a native part of Kubernetes. So it's all about an operator and YAML specs. But let's go forward, because one of the topics was about VMs. And VMs bring the need of storage into Kubernetes. That's why we love this. So what about running container? You're currently made, who's running containers in VMs right now? So running Kubernetes on top of a VM? Many of you, okay? And this is about how to run VMs in containers, so flip it. So why should you do this? Why should you run VMs on Kubernetes? One real-world example, today's applications often live in two worlds. This means your developers might already have created an application which is microservice-based, modern. It's the front end for your application. This runs on Kubernetes, but it still consumes databases, and these databases usually live in VMs. So this is two worlds. The application owners need to cover these two worlds. They need to request a VM. Open a ticket, I need a VM. Open another ticket, I need a database. Open another ticket, I need network access from Kubernetes to the database. This is what's blocking productivity from developers and from application teams. So why not bringing these VMs to Kubernetes? Maybe as a first step. And why not letting Kubernetes orchestrate these VMs? Meaning, in this case, you would have one point where you do the observability, where you do the troubleshooting, and where you can skip the IT silos. And you can integrate now the creation of these VMs into your DevOps automation, into the pipelines. You can create VMs using YAML specs. Put this into GitOps and just create these VMs. And this could also simplify. So you could also think about migrating VMs you already have into the Kubernetes world. Because then later it might be easier to take out the data service, which now currently runs in the VM, and run it natively on Kubernetes. And we also met some customers who have financial benefits from doing this. So maybe the virtualization vendor of your choice increased pricing or something. So this brought huge drive in this discussion. But now let's be a little bit more technical. Short recap, what are containers? Anyone knows what a container is? So it's a process within the Linux kernel. So all these containers share the same Linux kernel. They're isolated by namespaces. That's the concept of the Linux kernel. So to isolate processes from each other. There are different ones for mounting, for network, all these things. So you can isolate in many ways. They're limited by C groups. So this means they allow the process to consume an amount of storage, amount of memory and CPU. What's virtualization on Linux? Well, we might already knew because this project is quite old. It's KVM, the kernel virtual machine. If you want to run a virtual machine on Linux, KVM would be the choice. And that's on the market, I don't know, 15, 20 years now. Kernel virtual machine, it can turn the Linux kernel into a type 1 hypervisor. That's what the large competitor also does. A type 1 hypervisor means it runs on bare metal, and it uses CPU virtualization functions to run a VM. And this is integrated into the Linux kernel. That's just kernel functions, API functions in the kernel. And by the way, this question gets raised often. Yes, it supports live migrations. And yes, you can run Windows on it. There's a second project in this space, which is called QEMU. QEMU is an open source emulator. This can be used to emulate different CPU architectures. So for example, if you want to run ARM code on x86 or vice versa, you can use this product. So this can emulate, well, that's slow, but it's integrated into this ecosystem. And yeah, as I said, it supports and integrates with KVM. So if you run an x86 VM using QEMU, QEMU knows, okay, you're currently running on x86, so I don't emulate, I just pass over to KVM. So this is integrated. And it can enable emulation if needed. For example, if you're running on a platform which doesn't expose the CPU virtualization functions to the actual kernel, like an EC2 instance on Amazon, it can also emulate virtualization. That's not fast, that's not production ready, but you could do for testing. And there's a third component within the ecosystem. This is libvirt, and this is just an abstraction layer. It's a library, it's a daemon, it's a tool set to manage virtualization on Linux. As you see, well, that's the general idea of Linux. You have many parts which are best in class of what they are doing, but you need many of them and unite them. So that's the way how this is solved. Now, let's continue with the virtualization on Linux thing. These VMs being managed by KVM are started as a process, and they are using KVM, so kernel virtual machine functions. So basically, a VM being started by KVM is a process within the Linux kernel. And as I said earlier, processes can be restricted by namespace or isolated, and they can be limited by C groups. So could we just call them containers? It's a container starting a virtual machine using special functions of the CPU to virtualize. And now what about putting an orchestration framework around these containers? Could we call this Kubernetes? Obviously. So let's take a high-level look on what Kubernetes schedules. So if you have a container application, a pod, it's just, it's scheduling pods, which is a process containerized, limited, isolated. And this process, as I said earlier in the beginning, consumes data, persistent volume claims. Now on the other side, we have another process, which is a KVM process. And this is consuming a PVC, which is technically the boot drive of the VM. So this is the high-level view of how this works. Well, it's a little bit more complicated, but basically that's it. And there's a project called KubeVirt. Did I mention this earlier? Don't know. This project had the goal to integrate these functions, these capabilities of orchestrating these, let's say, special containers, VMs, into Kubernetes. So this is a picture of the high-level architecture of Kubernetes. The orange parts are basically Kubernetes things. So it's the kubectl command, it's the API server, it's the kubelet running on each of the nodes. And these have been extended by the KubeVirt project to enable Kubernetes to know about, okay, what's a virtual machine? Because it's a little bit special. It's not just a container. It needs some special handling. It has special features. So the purple parts are now these parts which extend the API server. So there's new API functions for these virtual machines, and I will show you some examples. And there's also some things which are running on the node side. So there's the virt handler, which is executed by the kubelet, and this per pod or per virtual machine instance, there are some processes being started. And you might see some of these things I earlier showed. So the picture hasn't been invented by me. This is from the KubeVirt project. You can see the link down there. But basically, if we take a look into these resources which now are being created on Kubernetes or which are now available in the Kubernetes API, the first and most important thing is the virtual machine. Yes, it's a YAML spec. Woo. So you describe a virtual machine, you can label it, you put it into a namespace. So basically, the virtual machine resource is describing on a high level, I need a VM. And this is all about these settings a VM should persist, which should live or which should be part of this VM. And as soon as you set this virtual machine object in the spec from running false to running true, KubeVirt or Kubernetes will create a virtual machine instance. So the virtual machine will be started. And this is the second resource we have, the virtual machine instance. This represents a running virtual machine on Kubernetes. This means if this is being started, the virt launcher pod gets scheduled, gets namespaced, gets limited, and now the VM starts. There's a live migration capability. So you can migrate these VMs. They live on one of the nodes, and you can tell Kubernetes, I want to migrate this to another node. Feature which is obviously needed by many virtualization people. And it respects the Kubernetes standard settings, so like node selectors, affinity, anti-affinity, taints, tolerations. So this is now all being, let's say, Kubernized. You can manage your VMs like you manage Kubernetes workloads. And this could be quite beneficial. Another resource, because I'm working for a data platform, Now let's come to data. We have another resource which is now introduced, a data volume, because VMs usually tend to be demanding on when it comes to storage. And the first thing which is introduced here is a data volume. A data volume basically describes where the VM comes from. It's like a template. And this template can, for example, reference a URL where you can download the image of the virtual machine. And if we take a deeper look into the settings of a virtual machine, and yes, I have a YAML ready to show you. When it comes to storage, VMs also have properties, and these can be of a type LAN, CD-ROM, virt.iofs, disk. So this means there are different ways to connect storage, because as you might know, if you create a virtual machine, you can attach an ISO image or other things. So this is also possible in Kubernetes. This storage or this disk of the virtual machine, this disk property, always references a volume. And this volume can be of type cloud init. It can be of type secret, config map, service account, so things you already know in Kubernetes. It can be of type persistent volume claim, so you can tell, okay, this disk, this boot disk of the VM or this data disk of the VM comes out of an actual existing PVC. Or it can reference the data volume I showed earlier, which means if the boot disk of the VM references the data volume, which then again references, we are Kubernetes, we're references a boot image, then at boot time, this image would be taken, would be created as a new disk, and the VM would just start. So just as a YAML example, this is my virtual machine. It describes, it's the kind virtual machine, it describes, gives it a name, it's running. And within the specs of the virtual machine, there's a part of the devices and the disks. And here the orange one says, okay, there's a disk, which is named root disk, and boot order is 1. So this is the first disk to boot from. And if we now take a look into the other orange pieces, there's a volume description for this root disk, and this references a data volume. And actually, the data volume then says, okay, this has been taken out of a data volume, which has been pre-created by this data volume definition. So this is actually the boot image. This is something you might need to get familiar with, depending on the Kubernetes distribution you're using. This can be hidden and abstracted, but basically, this is how it works. And there's another disk, which is the cloud init disk. So here, my example, I've been using cloud init to configure the VM, and this is just referencing then the user data stuff for cloud init. So this is basically how these storage pieces look for virtual machines. And in the end, it's just referencing PVCs. So it's just consuming Kubernetes storage. But there are some requirements for KubeVirt. The most important one is, if you want to migrate your VMs from one node to another, you need read-write many volumes. This means these volumes need to be able to be accessed at the same time from different consumers. This is one requirement not all storage solutions can fulfill. Usually, virtualization users, the consumers of VMs, prefer storage solutions which survive node outages and provide instant access to a volume after a VM failover. Just as an example, some default Kubernetes patterns won't work for VMs or won't be a good fit. For example, if you take a node into maintenance for your containers, the node is just stopped, or it's being drained, which means the pods are being killed and being rescheduled on another node. Now think of this pod would be a virtual machine. Do you want your virtual machines on one node running, being killed and started on another node? Usually not. So if you integrate this, and if you build this, you need to take care about these functions. And here, for example, if we as the storage provider need to do node maintenance because we need to restart or update our processes, we take care of this. We migrate the machine from the node we want to bring into maintenance mode, do live migration to another node, and then we bring our node into maintenance. This is some small details. Yes, there are differences. VMs are not pods. And this is something you need to take care of. But basically, the virtualization users, the consumers, want to have a reliable and performant data platform. So storage does now matter in Kubernetes if you run VMs on it. And this is where we come into the game. So we are the leading data services platform for Kubernetes. So we have a stable platform to provide a unified layer of storage in all of your Kubernetes distributions and in all of your platforms. We are agnostic to the underlying infrastructure, so we don't care what your compute and storage provider is. We consume whatever the platform gives to us, abstract this, and build on top of this a reliable, high available layer for storage, supporting containers and VMs. And we implement functions like disaster recovery, migration of data from one cluster to another, but we also take care about access, restricting access, protecting volumes from unauthorized access, and encrypting volumes. And we also take care about backup and restore. So this is all functions you might need when a non-VM Kubernetes environment comes into a, let's say, critical production, when data matters. But it's also needed when you run VMs on top of Kubernetes, because in this case, data matters. So just as a high-level example, what we can do on these platforms is async DR. Well, Kubernetes itself is a very reliable platform. So in a Kubernetes cluster, you have 3 replicas of the control plane. So usually this survives a lot of things. But for example, if you're running a Kubernetes cluster in a public cloud, or if you run it in your data center, it might happen that your data center goes down, even if it has 3 availability zones. Even if the region has 3 availability zones, a cloud region can go down. That's within the SLAs of the cloud. So customers running important stateful workloads in these clusters need a solution to have a disaster recovery. And what we can provide in a Kubernetes native way is the capability of replicating namespaces from one production cluster into another one, independent of the underlying hardware, independent of the underlying cloud, independent of the underlying Kubernetes distribution. So we can run this from an on-premise OpenShift cluster to an Amazon EKS cluster, or between different Amazon regions. And what we basically do, this is all again Kubernetes standard. First of all, we create a YAML spec describing how cluster 1 can reach cluster 2. This is about what are the endpoints, what's the authentication, what do I actually want to do? Give it a name. So it's a YAML spec. The second thing we do is we create a schedule, another YAML spec saying, okay, I want to do this every 5 minutes. And the third one is the actual migration, which is now namespace based, so your users can do them by themselves if you want, or if you allow them. Where you can say, I want the namespace with the Postgres, with the Mongo, and with this VM being replicated, referencing this connection between cluster 1 and cluster 2, following this schedule of, 5 minutes. And now we will snapshot the volumes on the left side, take all the Kubernetes or VM objects. Well, the VM objects are a Kubernetes object now, and we'll replicate them to the second cluster and create them there. So if you would take a look into the second cluster right now, you would see all the volumes, all the Kubernetes objects, but the only difference is the replicates will be scaled down to 0 because, well, they should not run because it's disaster recovery. And now if cluster 1 goes down for whatever reason, there's a single command you hit in the second cluster which will start actually your replicas with the last setting we know, and your production will go on. This is working for container pods as well as it works for VMs. So I think I also promised a demo, so I haven't prepared yet because it's always dangerous to do this live on stage. But we will invite you to a hands-on lab session. So if you're interested, just scan the barcode or visit our booth. There's another reason to visit our booth. I promised I tell. But first of all, if you want to do a hands-on experience on Portworx, subscribe to this session, where you will get an environment where you can test this. It's guided, so one of us. In September, it's a colleague of mine. In October and November, I will do this, and will guide you through how is this actually working? How does this look like, and how could this be integrated in your environments? So with this, I would like to thank you. Visit our booth if you want to win a C64, not an original one, a new one, but any questions?
Thank you, Daniel. So we have Slido, so you can submit your questions.
Okay, how is the default workload increased when using KubeVirt? So how does this influence the default resources? Well, basically, it won't put that many load into the control plane layer. So it's extending the API, but the Kubernetes API itself is very capable of being extended. So we technically, as Portworx, also extend the API. So that's not the problem. What you should take a look on is the actual consumption of the VMs, because VMs are not lightweight as containers are. So if you want to introduce VMs or KubeVirt to your clusters, first of all, yes, you can test in virtualized clusters and do this emulation thing, so to get used to get used to it. But in production, you need to run bare metal clusters. You need bare metal nodes. That's it. You can run bare metal nodes in the public cloud, by the way. So also Amazon has a bare metal node you can run. But yeah, you need to run bare metal. Take a look into the consumption of the VM. You can limit it very good because Kubernetes just brings capabilities of limiting this stuff. But that's, yeah, take a look on it. There's no number I can tell you, 5 or 42. Yeah, this is something to take care of.
All right. Thank you, Daniel. I think you are going to be around, so if people have more questions, I think.
So yeah, we have a booth in the hall out there. So and again, we do at 11:30 we will do a raffle for the 64. Mm-hmm. You're welcome.
Cool. Let's give him a hand and yep.
Thank you.